Okay, now that we know what a list is, how can we write an algorithm or a function to add some new capabilities to what we can do with a list? And often we want to know how many items or how many nodes are in a list, and we can implement a function that will be recursive to count the number of nodes in a list. So how might we do this? Let's try this, thinking through this in some pseudocode first and try and develop an intuition for the code we're about to write. So I propose this as a count algorithm. Given any list, if the list is empty, then the count will be 0. Right? This makes sense. If there's no items in the list, the count should return 0. Otherwise, if the list is non-empty, count will return 1 plus this same algorithm applied to any nodes left over in the list or the rest of the list, right? And so you can think of this as people standing in a line, and if you're counting off 1 plus however many there are people behind you, we could go all the way down through a list of a line of people. And when we reach the end, the last person would return, well, there's no people after me, but 1 plus 0 would be 1. And then the next person would return, well, 1 plus 1 is 2, 3, 4, 5, 6, so on and so forth. And we can kind of count up as we reach the back of the end of the list and move our way back to the front. So let's actually try implementing this in code. If you'll open up the O3 count app example, we're going to work with it. And what you'll notice right out of the gates is that we have a names variable set up where we are conning the strings Ramses and Roy together. And we're printing those names. So we see names, Ramses, followed by Roy, followed by null. And then we're calling this count function, count names. And our goal in this follow along is to implement this count function, right? So in a slide coming up, I'll explain what this T business is about, this diamond T in just a moment. But for now, let's ignore that and trust that this list parameter is going to be the list of names that we give it, right? So right now it returns 0, but let's add the implementation of the pseudocode that we were talking about. So if the list is empty, return 0, right? So if list is equal to null, return 0, easy enough. So this is the direct implementation of that piece of pseudocode. And this, by the way, is what? Can you remember the name for this condition in this segment of our code, knowing that this is going to be a recursive function? This would be our base case. Right? There's not any recursion that's going to happen when we reach the end of our list. We're going to say that we've reached a count of 0 because the list that we're trying to count is empty. Otherwise, though, this will be our recursive case. We're going to return 1 added onto the count process applied to the rest of the list. Right? So how would we express that in code? Right? So we're trying to add 1 to count applied to the rest of the list and return that value. So we can say return 1 plus count the rest of the list. Right? And so notice that this is a recursive function call. Right? We're saying count, and what we're giving the next invocation of this function call is an argument value that is the rest of the list, right? So if we first called this with Ramses and Roy, count would reach this line where count would return 1 plus count the rest of the list. So the second call to count would be just the list Roy followed by null, right? So let's save this and notice, sure enough, our count successfully was 2 because we had 2 nodes here, right? Let's try adding a third node to our names list. So if we add cons, say Kevin Gusk onto the front of names and assign the resulting list to the names variable, we now have a list where Kevin Gusk is followed by Ramses, followed by Roy, and null. And the number of names of that list was correctly 3, right? And so this is an example of a recursive function that's processing a list. So rather than working with numbers, which is another common case of recursive functions we'll see in Comp 110, we're processing a list here, right? And there's this natural pairing of, well, if we're trying to write a recursive function for a list, we need to be making progress towards our base case. And our base case, when we're writing an algorithm like this, is, well, when we've reached the end of the list, when we're out of items to process, right? When we're out of nodes to work through. And in this case, if we're trying to count the items of our list, we would return 0 at the end, because the count of the empty list is 0. But otherwise, what we're going to do is in our recursive call, we're going to take whatever action we need, we're going to apply whatever algorithm we're trying to assess to the first node. So we're keeping track of, hey, the very first node, we're going to count a value of 1 here. It doesn't actually matter what that value is, we're just trying to count up how many of them there are. So we're just going to say, we're taking care of the very first node of our list here by counting 1 for it. And then we're going to apply the same process recursively on the rest of the list. And because we're moving down the list and making progress towards the end, we're moving closer and closer to our base case. And so our conditions of avoiding infinite recursion are met here, right? We have a base case, which is the end of the list. In our recursive case, we're changing something. We're not calling count on the list itself, right? If we weren't counting, if we said, hey, keep counting this list, keep counting this list, keep counting this list, we would get a call stack exceeded error, right? Because we're not making progress through the list. This would keep counting, passing Kevin Guskowitz as the first node of our list, and we would never be making progress through it, right? So we want to count the nodes of the rest of our list and be sure that we're making forward progress. Kevin Guskowitz will call count of the list where Ramses is the first node, and that would lead to a call of count recursively where Roy was the first node. That would lead to a call of count recursively where null was there, in which case we reach the base case, right? So let me try and put a visualization on this, but I also want to talk about what is this special diamond T syntax, just briefly, because we're going to go into more depth on this on Thursday. But basically, this is an annotation in our code that's saying we can have, so you're going to see that when we declare a node, just like when we can say an array of type string, well, here we're going to need a different way of saying a node of some specific type, right? So in our code, you'll notice there's specifically a node and then string is the type of node that's we're saying we're working with. Well, if we want to write a function that works for a node of any type, what we're able to do is specify, hey, this function is going to work for a node of any type T. So this count function will work whether or not you give it a list of strings or numbers or some other type. Right? We'll talk about this in more depth. If that didn't make sense in a first pass, that's totally fine. I just didn't want to completely gloss over this little detail today. We'll come back to this. So this is a recursive function because count is defined in terms of itself, right? Either the list is empty and you have a count of 0, or you have a count of 1 plus counting the rest of the list, right? So if we wanted to trace through this in a visual sense, we could start with count, where we call it with Ramses, Roy, and Kevin. If we imagine what line of code would this evaluate to, and what return statement will be hit? Well, the list is not empty, so we would return 1 plus the count of the rest of the list. So we could say that we could substitute this, and if we wanted to use a substitution model here, we could substitute this first call. It would be exactly equivalent to 1 plus count the list of Roy, followed by Kevin, followed by null, right? Same idea, we can, if we went and looked at that call to count would evaluate to 1 plus the count of the rest of the list, or count of the list where Kevin is followed by null. That's going to lead to 1 plus count of the rest of the list, where the rest of the list is just empty. And when we reach the empty list, notice we're going to hit the return statement where return is 0, right? And so this is our base case. And once we reach the base case, that value is going to be returning back up and substituting with the function call. So 0 would replace the function call where we called count with the empty list. And now 1 plus 0 would be returned back to the call where we just called it with the list of Kevin. 1 plus 1 would be 2, which would return to where we came from before. And then finally, 1 plus 2 would be 3. And this would be the ultimate result of calling this function count with a list that had 3 nodes in it, followed by null. As I mentioned, when we're working with list recursion, we tend to have some complementary rules to like what we saw with numerical recursion. But specifically, we're always going to test to see if the list is empty. That means if the list is equal to null. And this is going to be a base case, right? This is when we stop recurring, and we know that we've reached the end of the list and our job is done. We need to start returning any values we need back up to the previous function calls. When we make recursive calls in recursive functions that process a list, we always want to be making forward progress through the rest of the list, right? We need to be sure that we're calling our recursive function on the rest of the list to be sure that we're making our way towards the base case and we can avoid infinite recursion in that way.